Hey, John here. Let's look at how the memory system works on our Z80. Up until now, we've kind of ignored these BA 15, 16, 17, and 18 signals that connect up to the 0.5 megabyte static RAM chip. I'm going to draw a diagram like this representing the context of that static RAM. All right. These signals here we're going to call a bank number. These are the most significant 4 bits of the address bus that is connected to our static RAM. As we'll see, if we make each one of these partitions, we break it up into 16 pieces, all right? Then each one of those is going to be 32K bytes, each one of these 32K bytes, all right? Now remember, the Z80 is an address bus that's only got 16 bits wide, all right? So the Z80 can really only address 64K of memory. Yet, we're going to hook up a 0.5 meg. So how are we going to do that? All right, here's how we're going to do that. Every single time the Z80 wants to talk to the memory, what we're going to do is we're going to decide which memory bank out of these 16 that interaction is going to take place in. All right, so in the simplest way to think about this, we could just simply set these values. Let's say we just hard code all these 4 bits to 0. What would happen? Now notice that BA15 is in here. Okay, where does that come from? Well, if the Z80 has 16 bits, right, its bus is A0 through A15. Now we're going to see that A15 here on the Z80 plays a role with this BA15 bit in this bank number. All right? So let's ignore this bit 15, this bit for a minute, and the most significant bit of the Z80 address, right? So this is the least significant bit of the bank number, most significant bit of the address bus, right? What about all the rest? Well, if all these are 0, and the Z80 is accessing any memory address at all with a 15 set to 0, that means that the byte address range must be from 0, 0, 0, 0 through 0, 7FFF, right? It's the low half of all the memory that the Z80 is capable of addressing. So this is what? A15 equals 0. Oops. Likewise, what happens if we just assume that A15 is a 1, right? And again, we'll see how that relates to here in a minute. Then your A0 through A15. When A15 is set to 1, the address that's being generated, if this comes from the Z80, must be 8000 through FFFF, right? A15 equals a 1. Okay. What else can we observe about this? All right. Each one of these 2 ranges of memory is 32K. Okay. So, in terms of 32K byte chunks of memory, 32K byte banks, all right, the Z80 can address 2 32K banks on its own. If somehow we provide these extra bits over here, it can access even more. All right, and that's what we're going to see that's what's going to happen here. So this is, how do we decide which bank to use at any one point in time? All right, that's how this is going to work. Now, what we're going to do is we're going to say, look, whenever the Z80 accesses the high bank, it's high, these bigger numbered addresses from the perspective of the Z80, right? These are greater than these numbers up here, right? So this is the high bank from the Z80, and this is the low bank. Okay? What we're going to do is we're going to build a circuit so that if and when the Z80 is accessing its high bank, no matter what, it will be using this 32K bank of the big memory region. Okay? And whenever the Z80 is accessing its low bank, we can let it refer to any one of these. And oddly enough, including bank number 15 up here, right? 0 through F is 0 through 15, right? 16 total. All right? It turns out it's kind of foolish for the low bank of the Z80 to refer to the same place, but yes, it's possible. We're not going to use it. It's kind of useless. On day one, what we're going to do is we're going to make this low bank refer down here to bank number 0. So if the Z80 ever accesses memory with an address in this range up here, 0 to 7FFF, that's going to mean the bytes that go from 0 to 7FFF in the half megabyte RAM here. Okay? If the Z80 accesses a byte at address 8000, it's not going to move up to here. What it's going to do is it's going to load it from this byte at the first byte in this bank way up here. And as it goes all the way up to its FFFF, it's going to move its way up in this bank, right? So 32K here for the low half of the Z80 address space, and 32K up here for the high address, and we're going to ignore everything in the middle for now, okay? If you think about that, there's really nothing wrong with it. It might seem strange and wasteful, but does it make sense from the perspective of the Z80? I submit yes. Why? Because there's 64K bytes of memory in this scenario. They're all different from each other. If the Z80 stores something at address, 1, 2, 3, 4, and then it reads it back from 1, 2, 3, 4, it will get the byte back that it read in. If it writes a bunch of bytes in progressively increasing addresses as it goes to like maybe 7FFF0 or and then 7FF1, 7FF2, and it keeps on going, and it's just walking through memory, and as soon as it reaches 7FFF and adds 1 to maybe a pointer in the HL register or something like that, and stores a byte at the next address, which would by definition be 8000, it would store it up here. So from the perspective of the Z80, it has 64K of contiguous memory starting from here through there and from here to there. And it doesn't know or care that all this other stuff is going on in here. Now, just as easily, let me change colors here. This low bank could refer to bank number 6 right there. Right? I mean, who cares? In that scenario, there's 32K of memory here that the Z80 will use whenever it wants the 32K, and it's going to think of it as being in this address range from the perspective of the Z80. And when it depletes that, if it's filling in with memory and it moves up to 32K, it then moves to the very next byte. It leaps again up to here, and the next byte in the rest of the other 32K of the most significant bank of 32K bytes in the Z80's view of memory, it will still come from up here. No problem. Okay? Same with any other one. The low bank can be any one of these things. And the way the circuit is going to be built that we're going to make here, the high bank will always be number 15 up here, bank F. Okay? And we'll see this is going to come in handy and make it easier for us to program. So what we're going to end up with is a system that what we're going to do is we're going to put the operating system code up here in bank 15. That's what we're going to do. And then once in a while, if it wants to run a user program, it can run a user program by loading it into bank 0, and it can execute instructions down here. In the simplest of terms, it could run another program by loading it into bank 1 over here, move this pointer so that when it accesses its low bank, it's using bank 1 instead of bank 0. And then it could run a program in there. And while this program is running, it can call subroutines up here in the operating system without a problem. And the operating system might say, okay, this program needs to wait for a while. Maybe it's, used up too much CPU, or maybe it's waiting to read characters from a keyboard, or for whatever reason. The operating system can say, all right, move the low bank back down here to bank number 0 and resume running this program for a while. Okay, so this is one way, in a really simplified example, to implement multiprocessing. We just simply load different programs into each one of these banks. All these different programs would share the code that's up here in bank 15, which would include the operating system. So if I'm running out of bank 0 in the simple case, and all the middle stuff is ignored, the big empty hole in here, we write a bunch of code. The code doesn't know or care about any of the other stuff in any of these other banks in here, these other 14 that are not visible to the CPU, because the CPU can only see 2 at a time, and in this scenario, it can only see 0 and 15, right? So he calls a subroutine, I want to print this, please. Okie dokie. He calls a subroutine that's up here in bank F. While he's printing, when he's done printing, the operating system can go back and resume this program where it left off, or it can say that program's run long enough, change this bank number that we're going to see is stored in a register to maybe D, and it can run some code in here for a while. And when it's done, it can change the bank to 9, run some code in here, and so on. Okay? So quite easily, it could just go round robin continuously, right? Really. I mean, it could run, 15 different banks of memory down here, all using the same operating system code up here in bank F. Alternately, what we can do is we can just leave one program in bank number 0. And it can use the operating system up here in bank F, and it can go back and forth all day long. And this program down here never really knows or, again, understands that these other banks even exist. Doesn't matter. Z80 doesn't know either, because the Z80 sees 32K and 32K, total of 64K, and it's happy. What do we do with all these other banks? Well, anytime we want, the operating system can put anything it wants in here, provided that when it does so, if it wants to resume running the program that's down here in bank 0, it sets things up so that bank 0 is the one that's used, okay, when it resumes this program. But what happens with these bits here is when this program is not running, and that happens every single time it ever goes up into the operating system to call a subroutine. I mean, arguably, what's happening down here doesn't matter anymore. What's happening then is up in here. If the operating system says, hide bank 0, instead of doing that, show bank number 1 for a little while, then the operating system can store scratch data and stuff into bank 1 while it's servicing whatever request was made by the code that was running in bank 0. And what we're going to do on the first draft of our BIOS is we're going to use these extra banks as a giant buffer cache for our floppy drive or the SD card. The SD card kind of runs slow. So anytime we read data out of the SD card, we're going to keep copies of all that data in all these extra banks, okay? And then when we're done, we're going to restore bank 0 so that any regular old user program doesn't know or care about all these extra cached copies up in here. So that if the program wants to read any data off the SD card that it has ever used in the past, and that'll be very handy when it comes to reading and altering the contents of the directory on the disk that gets read on and off constantly. And it slows the system down. They have to reread it all the time. Okay? So if we keep copies of all the system areas of the SD card, we can also keep copies of various user programs. It's not uncommon at all for the same program to be used repeatedly in one afternoon. So as it gets loaded the first time slowly, we'll keep an extra copy up in here. So if you want to run it again, it's already here. We can just copy the data out of these extra banks back down here at that time, which will go much faster than rereading it off the floppy or the SD card. All right? So that's why we want all these banks. in the short term. And in the long term, if you want to run like CP/M version 3, it will do this game where it can run many different programs and jump between them, like I said before. That's one of the things that CP/M 3 does for you. Okay, and this is one way to do it with a bunch of 32K byte banks. So we have a half a megabyte of memory over here. In order to address all those bytes, we need 19 address lines. 0 through 18 is a total of 19. Now, 16 of those can come from the Z80. Those would be named A0 through A15, right? So this is A14 here. This is not A15 from the Z80, okay? A15 from the Z80 goes over here. Now, if A15 in the Z80 is a 1, that means that the Z80 is referring to its high half of its memory, its high 32K bank. And if A15 is a 1 coming from the Z80 and we hook it up to these OR gates like this, it doesn't matter what's on these other signals, because if there's a 1 here, there must be a 1 over here on BA15, and a 1 on here, and a 1 on there, and a 1 from there, okay? So whenever the Z80 generates an address on its address bus, and the most significant bit is a 1, and therefore it's trying to address its own high 32K bank, these 4 bits will be 1, okay? Which represents bank number 15, right? 4 1s in binary is a hex F, which is 15, and these 4 bits represent the bank number. So these OR gates give us what we need so that the Z80 high bank is always forced into and will use, no matter what, the high 32K bank out of our static RAM. So that just leaves us what happens when A15 is 0 and the Z80 is accessing its low bank of 32K. All right. Well, in those cases, these bits are used to represent the 4 bits that go into the SRAM to select the bank number. That's all we got to do with. These 4 bits, as we saw earlier, come out of a latch down here. So how do we move around and tell the memory system which bank we want to use when the Z80 is accessing its low half, its low 32K bank? Well, we simply write a 4-bit value into this latch right here. Okay? These 4 bits are connected up to D4 through D7 on the data bus, and anytime we want, we can write a value into port number 10 over here, setting these 4 bits to whatever bank number we want, and it'll change the values of this until it's changed again in the future. All right? So if we boot up, remember earlier on I said when the system boots up and it wants to copy the flash into the SRAM and do the shadow bias and all those games, and I said, when that's happening, let's just assume these are just zeros, okay? The way these become 0 is that when we boot up the system, the first instructions in the flash code over here, what they're going to do is they're going to write zeros into that latch in address 10, so these all are set to 0, okay? That's how they get set to 0. We're going to do it with our own code. And because the Z80, by definition, when it gets a reset signal, loads the program counter with the number 0, we know that when the code is running in this flash over here, it's coming from the low 32K bank from the perspective of the Z80. In other words, this A15 bit happens to be 0 at that time. Now, we're running out of the flash, and it doesn't have any bank select logic involved in this. This only affects the static RAM over here, okay? So when we're running, starting at address 0, through the memory and the flash, fetching instructions and data and whatever's going on, first instruction is going to put a 0 on these 4 bits, at which point in time if we write any data into the static RAM, into the memory of the machine, we already went over this before, it doesn't get stored in the flash, it will get stored in the SRAM, and the address that it gets stored at will equal the 14-bit value from the Z80, the bottom 14 bits of the address, and because right now, when it first boots, A15 is 0 because all the memory interactions are down here at near address 0. It's in the lower half. Anytime we write any data into the SRAM, these 4 bits here, therefore the bank number will be 0. Okay? So, when we first fire this up, or anytime we press reset, okay, the flash will run. The flash will set 0. It'll store a 0 into these 4 bits. And therefore, if it writes into memory, any memory in the low half of the Z80 address space, it'll go into the bottom bank number 0 of the SRAM. Period. If we continue copying data out of the flash and we start writing it into the upper half, the upper 32K bank of the Z80's address space, then and only then will A15 over here become a 1. And this bank number down here will be ignored at that point. All 4 bits here will then be set to 1, and we'll be writing into bank 15, which is perfectly fine. So when this thing first boots, we put a 0 over here, and anytime we're writing into static RAM, we're either writing into bank 0 or bank 15, depending on which address we want to use that is being generated by the Z80. And we differentiate by looking at this A15 over here. Okay, so what do we have then? We have a coherent view of memory. We have 2 banks of 32K, and it may not seem logical, but who cares? As long as those 2 banks exist somewhere in the SRAM, and they're not changing underneath our feet, hell as well. We're using bank 0 and bank 15, no problem. Okay, when the flash is done copying itself to the SRAM and it toggles this reset logic up here by touching port number 70, resetting this circuit up here, it disables the flash from then on and enables the reading logic on the SRAM. The Z80 then is running out of the SRAM. Now, as long as we never change the value on these low bank bits, everything stays consistent while the Z80 runs the code. Okay? Now, let's say, for whatever reason, the Z80 starts executing code in the high bank, right? And it's just up there accessing instructions and stuff in bank number 15. Now, when the Z80 is up in bank 15, there's nothing wrong with it changing the value on these low bank bits. Okay? Because as long as it's interacting in bank 15, these aren't used for anything anyway, right? Because A15 up here would be 1 when, by definition, the Z80 is executing code and using data in its bank number 15. Because A15 is high, all these are 1s, no matter what we have over there. So when we are running code in bank number 15, it's perfectly reasonable to change this bank number down here and aim it somewhere else. After which point in time, if the Z80 starts accessing memory in its low 32K bank, it'll come from a different place than it did before we changed these, okay? So that's why I call this low bank A15, 16, and 17, and 18, because these 4 bits represent the bank number that's connected to the static RAM on these bits 15 through 18. Okay? These pick which of the 16 banks we're going to use when the Z80 is accessing its low half of memory. No matter what, it always addresses bank number 15 when A15 is high because these OR gates. All right? With this in mind, we can now boot up this system, set these to all zeros. In all honesty, it doesn't matter which bank you use in here, as long as you don't use bank number 15. right? Because if I set all these to ones, then when A15 is high, all these will be ones over here. And when A15 is low, they'll still all be ones, okay? That's the one case we don't really want to make use of, because the Z80 will get very confused, because its low and high bank will refer to the same thing, okay? So as long as that doesn't happen, it really doesn't matter which bank number is in here at this point in time, as long as you never change it and confuse the situation, right? As long as there's a bank to use when the Z80 is talking in the low half of the memory, fine. And as long as it's different than the bank it uses in the high half of the memory, that's fine too. And if you're careful and you're aware of it when you write your code, you can make both of the low and high banks of the Z80 point to the same place. It certainly will work. You're wasting half of the useful address space, but, yes, you can do that if you really want to. Turns out it's probably not all that useful, but something to keep aware of. You don't accidentally do it when you don't want to by setting these to some screwy value like all ones, okay? So that's how the bank select logic works. At this point, we can now start looking at how to boot this up and write code that runs out of the flash. Thanks for watching. See you next time.